Okay, today is lecture 10. It's last class of this course. Okay, so we need to finish topic of the spin-time coding, and also we are going to talk about the OFDM and MIME-OFDM. If we have a little bit of time, I can take you back to review what we learned in this course. I think today's course is very intensive. We have lots of the plan to finish in the next about 3 hours. Okay, so and also I need to remind you that our final exam has been scheduled, right? That would be November 26th. Is that right? Yeah, November 26th. And also the final project, and I think, let me check. We have also deadline in the final project. It's 22nd November. Just 4 days before the final exam, okay? And you can send me the email. I already got the inquiry how to upload the report. So let's go to the spin-time coding we discussed the last time. Skip this antenna diversity. We first go to the automotive code. If you look at the automotive code, it is a 2x2 matrix. So that means the information symbols are sent from 2 antennas and at 2 time slots respectively. So you could say we have dimension time. It means that the first row is the time slot 1, second row is the time slot 2, and we also have the space dimension. The first column is antenna 1, second column is antenna 2. Okay, so from there, so we can formulate this signal transmission model. You have the 2 antennas, and you have 1 receiver antenna. For sure, you can extend it to the multiple receiver antennas. I remember in one project report you are required to do the automotive coding not only for 2x1, probably 2x2, 2x3. That means if you have multiple antennas. So the only difference is that you just extend the signal. You have the R1, R2, R3, R4, R5, R6, similarly, right? And then you can get this signal model. And then after some manipulation of the signals, especially for the second received signal R2, we take the minus, the negative, and then conjugate so that we can swap the channel matrix with the signal matrix, so we can get this equivalent equation 2. And then for the equation 2, we can perform the decoding by left multiplying this Hermitian of the matrix H, so that you can see this matrix actually is orthogonal matrix because each channel H has the same format. Look at this one, H in equation 2 is the same, has the same format with the code matrix in the equation 1. That is Alamotti type. We also called orthogonal code matrix. So orthogonal not only for the real signal, but also for the complex signal. So that's why we, in the second row, you see we have the star. So that is conjugate. So I mean that this is a orthogonal called complex orthogonal code matrix. And then this channel matrix here is also complex orthogonal matrix. Orthogonal means that this matrix left multiply with its Hermitian, so it will give the identity matrix. So that's why you can say here, it gives this one due to this property. It gives the identity with a scalar, a constant, so that is called the orthogonal matrix. Due to this orthogonality, so equation 3 can be deduced. The equivalent to say that this is y1 equals as1 and y2 equals as2. So it means that equivalent to say that we finally perform the coding. The s1 was sent, then we get y1 onen. 2 was sent, we get y2 onen without any interference each other. So that's the significant difference from the R1, R2. Look at R1, R2, you have the interference, right? You have interference from the other antennas. But now, after some transformation, when we get Y1, Y2, so it's a very clean signal. Y1 is corresponding to the S1, Y2 is corresponding to S2. There's no interference to each other. So that is I think that is the simplicity of this decoding. And we call the ML detection of the automatic code can be decoupled into the 2 independent decoding of each symbol. That means S1 you can perform the ML decoding. S2, you can perform SI decoding separately. So that is the complexity very low. I think that's what we discussed last week about the automotive code. And next, we are going to go deeper about the performance analysis of these MIMO channels. I think this one, I need to give you some of the introductory about the foundation knowledge of this Q function. Because this is the first step to perform the error analysis. So because the error rate function, Q function are very critical. So that's why I need to let you know this one. Probably you heard about this. So first, this is pure statistics. Okay. First, let's consider the X, that is the random variable, follow the Gaussian distribution with zero mean and univariance. And then look at this one. So the Qt function equals probability x larger than small t. I can draw the whiteboard on the right-hand side. You can see clearly what does it mean. Let me see. Just a second. Connection got the problem. Okay, good. It's like the we have the Gaussian. Let me move around. Okay, so this is like the Gaussian random variable with zero mean and the univariance, and we see this is the X random variable. Oh, what happened? Let me add a new page. Okay, so this is a random variable, and this is PDF. It's like the Gaussian PDF. And then we say that this is a probability x larger than small t. T is a constant. So firstly, we just determine the t values. Here is t value. For example, t could be positive or negative. You just choose one. And x larger than t, what's that probability? So the probability x larger than t equivalent to say that the region on this part, so the shaded area under this is the curve of the PDF from t to infinity. So that is called the probability of the x larger than t. Do you understand? This physical meaning of the probability x larger than t can be denoted by this area, integration of this area. So that is called the this probability. And also you can look at the lecture notes that mathematically it can be calculated by taking the integration of this PDF function from t to infinity. The PDF of the Gaussian is given by the 1 over square root 2 pi with the exponential of the negative half x squared. and then you take the integration from t to infinity is equivalent to, say, this probability, right? But the question is that this integration cannot be solved because not all the integration can be solvable. So this integration cannot be solved. So then we have to look up the table, or we call that one special function. We have many special functions, like the Q function is one of them. We have the gamma function. We have the Bessel function. We have many other functions. So it means those special functions cannot give any exact value by calculation. So you have to look at either by using MATLAB, by using programming, or by the lookup table, then you get the values. So that is a case that is called the Q function. So for this one, we can say it can be simplified as called QT. QT, called QT. Once you say QT, then immediately in your mind you should get this picture. So QT means that, okay, this is called the tail. The shaded area is called the tail part of this Gaussian PDF from t to infinity. So that's called the QT function. Okay. For this QT function, there is the such called the Chernoff bound. We don't need to prove it. So that Chernoff bound, that's a kind of the inequality called Q. That is Qt smaller than exponential half of t squared. So that is just an inequality. You can just keep it in mind because later we are going to use this as a property. We don't need to prove this. The mathematics, you can try, but we don't need to prove this so far. And then you may wonder, this only for the Gaussian distribution from 0 to 1 with 0 mean and unit variance. So how about the general Gaussian PDF? How about we have the Gaussian PDF with mean value as mu and a variance sigma square? How about that? Can we also use this Q function? Yes, we can do that. So, but the first step, you need to normalize this is a random variable to be the same as this normal distribution with 0 mean and unit variance. So that's why here we need to define. So you can look at the, let me try it. Okay, so if x follow the Gaussian distribution with the mu value, the mu as the average value and sigma square as the variance. So what happens of this Qt? Right? You may wonder what is that probability. How about the question is what's the probability of x larger than t? Definitely it's not Qt, right? Before we get Qt on the condition that is the Gaussian follow the normal distribution with 0 mean unit variance. But now its distribution changed. So definitely it's not Qt function. So we need to make some the equivalent change. That means we can define this equation y as x minus mu over sigma. We can define a new random variable y equals x subtract its mu value and divided by the sigma. Okay. For this one now, if you look at y, the distribution of y, so now y here follow the distribution 0 mean and the variance of 1. It's called normalization. Why? Because x random variable has average value mu, so y just subtract this mu from this x, right? And then the average value of y is 0. And the variance of y is also got the 1 because you divide it by the sigma, and then the variance of the x is the sigma square. So then you can say the variance of y is 1. So that's why we got this 0, 1 normalization for the random variable y. So if y have such value, so then we can further do this step. That means probability of x larger than mu over sigma larger than t minus mu over sigma, right? Because from that probability, we just do the same thing on the both sides. And then we can say this is the probability of x minus mu over sigma, that's random variable y, larger than t minus mu over sigma. And remember the probability, the y random variable has the normal distribution, right? So then you can say this one, you can call the t prime. is like the new t value. So then this one is called qt prime. That's also called qt minus mu over sigma. So that is the answer. This is the equality sign. Okay. So it tells us that for any distribution of the Gaussian, so we can first step normalize this random variable to be the zero mean and the unit variance, and then we can still use Q function. So that is the general answer. You look at the left-hand side. So here, probability x larger than small x, you can change it into t, doesn't matter, right? So then it's like the constant. So that equals q t minus mu over sigma. So that's what we just derived. Okay, so it tells us that for n PDF, because later when we analyze the error rate, so we will frequently use this as equation 6. So that means that when we make detection, we want to find out the detection error. Detection error occurs when that probability x larger than threshold. So that's equivalent to the equation 6. So that's why here I just put some prior knowledge before we go to the deeper analysis of the error. Okay, so these are some of the information paper, okay, for you. In the MATLAB program, so there are another function called error function, ERF. So if you can type in help ERF, it gives this formula. So ERF has some relationship with the Q function, not equal to each other. So ERF equals like this one, Q equals this one. I think that is the old version, but current version may have Q function already called Q FUNC. You can type the help Q FUNC, Q function. Then you can find this Q function, do the programming, okay? So this is prior knowledge. So next, we are going to analyze the error rate, okay? So firstly, I need to give you some of the definition called PEP. PEP means a pairwise error probability. Pairwise, you can see that we have the pair, C and C hat. C hat means that originally a code, you can imagine this is like some information symbol or matrix or package. You want to send this package, C, this is real, that's true signal, to a receiver. So after this transformation at the receiver side, you got some version of this package, and that one definitely is corrupted due to the noise or interference. Not the same as before. So we call the C hat, right? So that means you got the C hat. But C hat and C could be the same, could be different, because you try the best, you want to decode the signal, okay? You try to recover the original C. However, there is a likelihood you may get it wrong because you got the C hat. So that's why we call C hat is like the estimation or detection part of the C. C is the true value, C hat is the detected one. It may be true, may be false. And the PEP is defined that when C hat is not equal to C, we see there is detection error, because I still want to use whiteboard so you can have the visual image about what I say here. So this C through the transmitter and send out. Okay. And at a receiver, so you also perform the decoding. For example, decode, and then you got a C hat. So this very brief, okay? You just say C is original information symbol or code matrix, anything. After modulation, transformation, or any system, is sent out to the antenna. At the receiver side, through the wireless channel, you got some signal. You try to filter out the noise. You try to detect the signal. You got a C hat. If you compare with this thing, C hat not equal to C or yes, so that's called detection, right? Because you need to make sure this is correct or wrong. So that's called comparison. If you find that they are different, we say they are wrong. That means your detection is wrong. So that you just count, right? Take a count 1. If you count total number of the mistake, and then through all the transformation times, so you get the error probability. So then this is the PEP is defined. PEP is defined to find the probability. That means C go to C, I mean it was sent, and the receiver it will detect a C head. If they are different, they call the error probability. Okay, that's definition 7, equation 7. And equation 8, that is the total error probability by considering all the possible transformation of the signals. So what does it mean? It means that the C may not be unique. Maybe you have the different code or signals, C1, C2, C3, C4, for example. And for example, you say, if I send C1, it maybe go to C1, that's correct. If I go to the C2, C3, C4, you will see they are all wrong, right? That means in the detection part. And also, similarly, if you send a C2, let me see. You cannot write. Yeah. And go to C1, that is wrong. Go to C2, that's correct. And 3, wrong. C4, wrong. So that means you may have sent out the different version of the signals. Okay? So then you need to consider all the average. That means average error probability. For example, if I send say 1, so how many cases I got it wrong? Okay, that means you got C2, C3, C4, you will get mistakes. Then you count the number, and then take the average. So that's why you can see here, I take the average probability that when I send C1, I got a different CK, K not equal to N, right? So then you will get error probability. And then on the average, divided by the total number of the signals, that is called the total error probability. So that's still the definition. I just want to try to explain to you. Okay, so now we got to the real stuff. We need to analyze the error probability from MIMO. Firstly, look at the channel model 9. R equals CH plus noise. First, I explain to you. R is a received signal vector. C is a transmitted signal called a matrix. H is the channel vector, and N is noise. You may wonder, how do you get this equation? Okay, so let us say the equation 1 here. You will see how I can get this equation. For example, if you remember, we use automatic code. We send S1, S2 at the same time from 2 antennas, respectively, and then we send minus S2 conjugate, S1 conjugate through 2 antennas, respectively. So that's why we get R1, R2, right, at the receiver side. And then that's why we can rewrite that R1, R2 in a column vector so that we can get this expression. So you see, this is for brief brevity, you see this is R equal C times H plus noise. C is automatic code, H is channel vector, H1, H2, noise is not a vector. That's it. Okay, you just bear this in mind. R equals CH plus N, that's equation 1. I just want to give you a simple example, right? If you have too many antennas, probably you got confused. How about we just consider these 2 transmit antenna, one receiver antenna. So that is equation 1. So now you can say, okay, we got equation 9. Equation 9 is just equation 1, okay, for simplicity. But the equation 9 actually it can be general, can be any number of antenna. I just want to make you feel comfortable that by considering equation 1 for the simple example, by focusing on the 2 antennas and 1 receiver antenna, that's it. That's equation 9, okay. For equation 9, remember, we send a code word C, right, from the transmitter side, through the channel H1, H2, that's called channel vector. Crowded by the noise, then you got the received signal R1, R2, right? That's the equation 1 I just mentioned. CH plus noise, okay. Then in the receiver, what we try to detect the signal. We try to detect signal S1, S2. If you are lucky, you got the total correction in the S1, S2, then your detection with C hat equal C, right? Because you make the S1, S2 both correct. But in some cases, you may get S1 detection correctly, but S2 wrongly. Then if you look at that code word C hat, definitely not equal to C, right? Because there is one mistake in the S2. So that makes the two code words not identical. C hat not equal to C. Or you may get the S1 to be wrong in the detection, then also the C hat is not equal to C. Or some cases, the worst case, S1, S2 are both decoded wrong, then your C hat is not equal to C. So you can see that many cases, that is a detection error. You can get this one. And then we're trying to say, okay, for the given channel H, that's simple. I just want to say H1, H2 is given. I don't want to consider the fading so far. We want to simplify the problem. H1, H2 is given. So what is the probability you send a code word, Holomotic code, say, however, at the receiver side, you got a mistake. The mistake occurred when S1 or S2 or both are decoded in error, right? So that probability is given by the equation 10. You may wonder how. That's later we can go step by step. Just in the first beginning, you should understand why what we are trying to do here. We try to figure out the error in the detection. We send a code say, we want to find out the error probability when we make the detection of C, which is not identical to the C, okay? So that's why we can get this. That's the left-hand side. We need to start from the left-hand side to go step by step in the mathematics. And then finally, we can get to the right-hand side of equation 10. So that's called a proof, okay? So this page only gives you the major results, not the proof. Okay, so equation 10, that is the first major result. That means for conditioned H1, H2, you send a code word say, you got the different code word C hat, then error probability occurs. That is equation 10. Equation 11, that is another case. Equation 11 means that how about we consider channel is a complex fading. Look at here, H. It's not a constant. Previously, it's called given H. Given H means that H is fixed. H is constant. But here, H here is a random variable and follow the complex Gaussian random variable. That means H1, H2. Remember, H is a color vector, right? H1, H2. And both H1, H2 are complex random variables. Follow the Gaussian distribution, like 0, 1. So what's that, the error probability? So actually, in another word, this channel actually is Rayleigh fading channel. Rayleigh fading in mathematics, that means the H coefficient follow the complex Gaussian, right? Then we call that Rayleigh fading. You may wonder why it's called Rayleigh, because its magnitude follow the Rayleigh distribution, but its complex coefficient itself is still complex Gaussian. So it means that I can put here that this one, H, if we consider H here is H1, H2, right? We have the two vectors. We have a vector of two elements. For H1 or H2, H1 is a complex Gaussian, 0, 1. So that is a Gaussian random vector and complex. That means H1 is a complex value, complex random variable. It has its own real and imaginary part. H2 the same. But you may want the magnitude, the H1 or magnitude H2, they follow the Rayleigh. Rayleigh, R-A-Y, I cannot write here. It's stuck. It's a lost signal. So its magnitude called the Rayleigh distribution, if you look at the right-hand side here. So that's why we call it Rayleigh fading. Sometimes you say, okay, this is Rayleigh fading, what does it mean? It means that it's H, the complex channel coefficient is a Gaussian random variable, and its magnitude is the Rayleigh distribution. Okay, Rayleigh distribution actually has its PDF. It's a Rayleigh PDF. Okay, we come back to say the equation 11. So we say that H is, look at it, H is a complex Gaussian. It means that its magnitude is Rayleigh distribution. So that's why we say Rayleigh fading. So how about the Rayleigh fading? Then what's error probability? You see this is error, and that will be more critical or challenging. Previously, you say H is given, so we can calculate equation 10. Now, based on equation 10, we say H is random. So what you are going to do is that you need to take another integration over the PDF of the channel of the equation 10, right? So then you can take the average. You can take the average of this error probability for different value of H. So that's why you need to take the PDF. So then the result is equation 11. So here is mainly results. We have not gone into the details. So it just gives you some of the major results. This is the major proof, 1, 2. Firstly, constant channel. Secondly, it's a Rayleigh fading channel. What other probability analysis? So results are given in 10 and 11. So next, we are going to go to the detail how we can prove it. Okay. If you look at the proof, we have only, I think we have only 2 pages. Look at it very simple, but I think it takes some of the knowledge, advanced knowledge regarding the mathematics, statistics. So let's see how much you can understand, but this is really critical, okay? So 3 pages, I think, right? So firstly, we need to start from the left-hand side, right? Equation 10, left-hand side. So probability of the C is mistaken detected as C hat. So now you need to truly understand the physical meaning of the wrong detection or detection error. So why this detection can be made in error? What happened? Otherwise, you cannot write beyond this step, because the first step is the probability C go to C hat. What's next? If you don't understand this detection error and you don't understand how it can be in error, then you cannot go further step. You'll be stuck in the first step. Okay, so let us see. C go to C hat. Firstly, this is regarding to the detection, all right? So I need to give you some knowledge of the detection theory. If you studied TELE9754 in the last term, probably half of you have studied that course before, then you may feel comfortable. You say, oh, I understand what's the meaning of the detection or ML detection. If you never studied that detection theory, you say, okay, this is quite new to me. So I add a new page to talk about the, let me see, the new page, to talk about the detection. Let me see. Okay, so here I'm trying to say detection, ML, where is the writing? Cannot see here. Okay. ML detection. ML detection, that means called the optimal detection, called the maximum likelihood detection. Especially when we talk about the signal 1 equal x plus noise, and yeah, you can say that. That noise is Gaussian distribution, usually it's a Gaussian distribution, okay? So 0, 1 something or sigma square if you have some the noise power. So especially for this model, we send a signal x, and x is corrupted by the noise. We got to receive the signal y, and then we try to recover x from the observation y. So how? What is the best strategy to make this detection? So that the best one we found out that is to make, if you say that is to minimize this x, we call the square, the norm square, or simply say that the distance. To make sure this is distance to be close as possible, that would be called the optimal detection. So that's a very simple one. Okay, you may skip all the details of the derivation, but this has been already proved to be optimal. In the TELE9754 we have the one class talking about this derivation. So the simplicity that you can say without noise, y equals x, then 1 minus x equals 0. That is best. The minimum, that means we want to find out the minimum distance or nearest neighbor. So sometimes the ML detection, maximum likelihood detection, is also called nearest neighbor detection. So that means we want to find out which one is the nearest. So I'll give you an example. So if x is QPSK, QPSK like this one, you have 4 different signals, right? This called the 0, 0, 0, 1, 1, 1, 1, 0, right? You have 4 different candidate signal. In the modulation part, in the signal, you transmit one of them, right? According to the 0, the pair of the 0 or 1, right? If the double 0, you choose the first signal S1. So that's the 0, 0, and 0, 1, 1, 1, 1, 0. And this called the S2. It's just lost signal again, don't know why. Okay, this is S3, this is S2, this is S4. You have 4 different signals, and according to the bit mapping, is a 0, 0 or 1, 1 or 1, 0, 0, 1, you choose one of the signal to be sent out, right? It's called the QPSK. You should remind me, because I see the screen different from what you see there. I don't know why. Let me see. Okay, so I think this is clear. QPSK signal, you have 4 candidate signal, right? According to the bit mapping 00011110, you choose S1 or S2 or S3 S4, is that right? So that's why. And then you got the 1 equal S plus noise. For this, for the observation, if you look at the observation Y value, so from there you cannot say what is S1, S2, S3, S4. You don't know, because you try to, from here, you want to make the detection S, right? You really look at the observation Y value. If you want to map this observation value into that 2-dimensional plane, Y may be here. Maybe this is the Y. What happened? Use color here. This one, for example, is Y value. You can say Y may be there, because it's shifted by the noise. 1 equal S plus noise, right? But based on the observation Y, you can find 4 distances. D1, this is called D2, this is D3, this is called D4. You have 4 different distances from the 4 different signals. And then which one is the closest one? For sure it's S1, because the observation value lies in the first phase of the 2-dimensional plane. So it's closest to the S1. So from here we say S hat equal to S1. So that is called nearest neighbor detection. So usually you just based on observation, and then you say, okay, the transmitted signal, maybe there's 4 of them, so let's find out the distances for each one. Then which one gets the shortest distance? That's called the nearest neighbor. That is the best optimization, the best estimate. So then we make the detection as head as equal S1. If one lie in here, so obviously you say the detection will be S3. Okay, you may wonder, is that good? Yeah, you get a mistake, but on the average, that error probability is minimal. So that's why it's called optimum detection. Optimum does not mean 0 error. Optimum means that it's a minimum error on the average. You cannot find another method which is better than this one, or to have the minimum smaller error probability. No, you cannot find another one. So optimal detection means that on the average, it can achieve the minimum error probability. So then the nearest neighbor, the minimum distance, is the best estimation method for the signal or detection signal. Once you get this knowledge, then let us say the lecture note about you transmit this one. You transmit C, you got a C head. Now you may wonder, so I transmitted C, why I got a C head? What happened? And usually, then you need to, from previous example, you need to compare the distance, right? So let us say another page, add another page. Okay. So you remember R equals CH plus noise. Does not show here. Let me see. Okay. Yeah. This is the model. I just mentioned is equation 1 or equation 9 is the same, right? And we want to say that if we move this, if the get the C hat, it should be that the C hat should be get the minimum distance of the R minus CH. That's one. So that means you got the observation R, and you got many candidates of the C. Let me try to give the different color. C here is a true value, but you at the receiver side, you don't know that which one is the true value. Okay, so I think we have the limited screen here. Okay, for the C, that is the true value. I don't know, but for the receiver. At the receiver side, it only knows the R. R is known. H is known, right? R is known, H is known. C, I don't know, but I know the set of C. I know all the possible set of the C, like the automotive code. C is S1, S2, minus S2 conjugate S1 conjugate, right? And for S1, S2, if they are QPSK, you just choose all the possible QPSK signal into that matrix. So that totally how many combinations? Probably 4 power 2, that is 16, right? 16 different C value, C matrix. Do you follow me? That means C here is an automotive code, S1, S2, minus conjugate, S1 conjugate. And for S1, it's 1 as QPSK, S2 is also QPSK. I cannot write, I don't know what happened. Okay. So you have 2 QPSK, and then if you look at the combination of C, how many totally different version? Yeah, for S1 you change different S1, and then you change the 4 different S2 value. Then all together, you will get a 16 version of the C matrix, all right? Because you put, every time you change S1, into another signal. Because QPSK signal, you have only 4 possible cases, right? So this one, you have got a 16 combination. So that means this is from the set of the C. From C1 to C16, okay, you list all of them. And then what you do is that you just measure each distance. You substitute each possible set of C into that equation. R minus C1 each, R minus C2 each. You calculate, totally you got a 16. And find out which one is the minimum. So that is the best one. Okay, so that is the ML detection of this alarmotic code. I mean, that's what I'm talking about. So, because here, but you may wonder, in which case we got the mistake? Because this is the correct answer. Yes, we can get some error. As I mentioned that before, that we want to find out the minimum distance, right? And the minimum distance, we hope, once we get the minimum distance, and then that C hat equals C. But that's our wish, right? This is called a wish. Then that is all perfect detection. If we can find out this C hat equals the true value C, okay, you got it. That's correct detection, right? Because that's not easy. You have 16 different C versions. You need to find out one of them to be correct, and 15 of them are wrong, right? So that's not easy one. But if you get it correct, okay, that's the perfect detection. If you get it wrong, what does it mean? It means that when you get that estimate signal, so that distance actually is smaller than the distance for the real signal. So in other words, I can show you here. We have different versions. For example, QPSK is still same thing. We see the y, if you remember the previous example, we see the distance to be here, that is called S1. That is correct detection, right? This is the previous example for these QPSK signals. But sometimes I told you, okay, S3 was sent, but your observation Y is here. Then follow the ML detection rule. You say Y observation on the phase 1, I will make it detection as S1. But I told you S3 was sent. You are wrong in the detection. Okay, that's the best I can do. Because S1 was sent, observation Y is far away from the S3, Y is here. And Y is mistaken as S1 in the detection, so you got a wrong detection. It happens. So what does it mean? In this case, it means the distance Y minus S1 definitely smaller than the distance Y minus S3. So you say S1 was detected. Is it right? From this example, S3 was sent, you got observation Y, and then distance Y and S1 shorter than the distance Y and 3. So that's why you make detection as S1. Unfortunately, in the beginning, S3 was sent. So that is one case of the error. Okay? So now, from this example, I just want to explain to you why you can get a detection error. That happened, although this probability is very small, very, very small. But it happened theoretically. Okay? You see the Y is far away from S3. Usually S3 was sent, Y should be around S3. Okay? Should be around, because the noise is not so big. If not very big, yeah, Y may be deviated from S3 with a larger distance if you consider the Gaussian PDF, right? So that means the Gaussian is not, has a larger variance, and then there is a high chance of this some value Y value is far away from S3, okay? So that is possible. So that's the one case. Y is far away from S3, so that you mistake Y as S1, you get the wrong detection. Now let's go back to C here. So if we got to C hat is not equal to C, what does it mean? I'll give you a page. Cannot I can move a page here. Let me see. If C hat not equal to C, what happened? What does it mean? If C hat not equal to C, it means that, remember what's the C hat? C hat on the above, look at the above the space. Let's go back a little bit. C hat is equal here, right? If C hat not equal to C, what's the meaning of that? It means the distance between R and C hat H is smaller than the distance and R and CH. I write this sentence. That means the distance R minus C hat H smaller than distance R minus CH. So that you because this distance is smaller than CH, so you make detection at the C hat, right? So that's why you get the mistake in the detection, because the true value should be C. However, in the detection part, you measure the distance, and C hat is closer to the observation C, observation R. So that's why it's very similar to this example. So you can get this mistake. So in other words, the probability of this equal to the probability C go to C hat for a given channel. Channel here is constant, okay? So that means C go to C hat because you choose C hat as the optimal one, and optimal one is not equal to the true value, so that's why you got the wrong detection. You may wonder why I get it wrong in the detection, because you measure the distance between R and C hat H, which is the shortest one. You assume, okay, shortest one, because I got a golden rule. The golden rule, the ML told us that if you find the minimum distance, that's the optimal detection. Okay, I follow this rule. I found out C hat H is the closest to R, then I thought that's the best one. Yes, that's the best, but not correct in this case. I mean that ML is optimal detection. That doesn't mean it's always correct. It means that on the average, it has the highest detection probability, the minimum error probability. But in some cases, it can happen, it can occur. Some error can occur. So that in this case, yes, it's one of the error. You make detection, the C hat is very close, and then you follow that rule. You say C hat is my detection. And C is a little bit far away from the true value of R. So then that's why here you say the distance here, this is the minimum distance. And this one is bigger than that one. So that's why you choose the C hat, not a C, right, in the detection. So then you say this is the probability C is mistaken as the C hat can be explained as this equation. So this first step is very, very important. Otherwise, you cannot go deep, go next. Because some students only are stuck into this step. I don't understand, C go to C hat. What's the next step? The next step is that measure the distance. R and C hat H. Their distance is shorter than the distance between R and CH. So that's why you make the detection at the C hat. Okay? So that's step one, very, very important. I think I spent a lot of time talking about this step. Then once you can get this correct understanding, I think only step one is very critical. So all the following, just mathematics, okay? Only step one here, regarding the detection theory, you need to understand what's the optimal detection, nearest neighbor, why I choose the nearest neighbor, I still can get error. Yes, some cases, I mean, some cases with a very low probability, you can get the wrong detection. That not mean zero error, but it's still best method, it's still optimal detection. But in this case, you got a mistake, C hat, because the distance you found out is minimum. R minus C hat H is minimum, okay? So that's why it's a probability. Once you can get here, if you look at the lecture note, get this step. It's the same as I just mentioned. Then next, I will explain the detail with mathematics, okay? I think I can take a break. Then we can come back to talk about the mathematics. Okay, so let's continue our effort. So I think the first step, I tried to use 30 minutes to explain the first step, why we had this error probability, okay? And then the next, I think that is just the mathematical derivation, so I can use whiteboard to continue our effort. So let me see. Next, I also want to take you to study some of the basic mathematics, because all the following are based on the mathematics, okay? First, we consider a complex random variable, x, okay? This is a complex one, x. The norm square actually is given by the x, because this is one signal, right, or one symbol, so it could be given by the x Hermitian. If the, let me see, if x is a column vector, so we can swap. X Hermitian times x. So here x, I can give example. X is x1, x2. x1, x2, so this one means that X Hermitian is S1 conjugate, cannot write what happened. X2 conjugate and x1, x2 equals x1 square plus x2 square. Can you follow this one? This is called norm square. Norm square is actually is the x1 magnitude square plus x2 magnitude square. And if you can follow this derivation, so firstly, x is a vector, column vector, and element x1, x2 are both complex. So that's why I use x Hermitian times x. As Hermitian is the transposition and then conjugate. The s1 x star, s2 star times x1, x2 equal this one. Okay, this is called norm square. No question, right? Okay, good. So based on that, so we can try to calculate this one. Okay, so let me see. I move a little bit. Okay, so let us see. Probability R minus C hat H square smaller than R minus H square H. Okay, firstly, we know that R equals CH plus noise. Then let us see. Okay, we first define delta equals C minus C hat on the left-hand side. I just forgot this one. We call this one as the the difference between the two code words, because we mentioned that C hat is not equal to C because we detected it wrong. So that is why the C hat is not equal to C. So that means delta is not 0, right? So then we call the delta as a code word difference. In that case, also we know that R equal, let me try to figure out, R equal CH plus noise, that's the original model. So equation 9, given this model, right? So then next we are trying to simplify this equation, okay? And then you can see on the left-hand side here, we substitute R equals CH plus noise, so that is CH plus noise minus C delta H square, all right? Can you see that? Yes, the step. Smaller than R minus CH, that is N square. Is that correct? Can you follow me here, right? So far, you see this is R. CH plus noise is R. R minus C hat H. That's the left-hand side, okay? Right-hand side is N. So next, we make this, we further simplify. I'll give some more space. The probability, and this one, it's a loss detection. Okay, because the CH minus C hat H, that is called the delta H plus N and square smaller than N square. So this is N. Can you see that? Is that correct? Because CH minus C hat H is delta H. Okay? So you got this step. So far it's fine, right? Okay. Next, we simplify this term. The delta H plus N norm square. Remember, in the above, somewhere, we derive the x, let me see, go to the above, we use that property. This is a column vector, so this one equals S hat H, x, H times x, right? We can get this step if you remember this one. So, and the delta H plus N, and you can see that's given by the delta H plus N Hermitian times delta H plus N. Cannot write what happened. Yeah. This one smaller than N norm square. This one is I write the norm square equals its Hermitian times itself. You can just regard that like x. That's x Hermitian times x. Is that correct? Because I see you nod, so you should be, you can follow, okay? So next, I multiply one by one on the left-hand side. This one multiply each one, it's done. So what do we have? We can move a little bit lower here. Okay, on the left-hand side, delta H Hermitian times delta H, that is delta H norm square, right? Delta H Hermitian times delta H, like x Hermitian times x is x norm square. We just mentioned that, right? And n Hermitian times n is n norm square. So I just write this one is n square. And also we have delta H Hermitian times, we have another two terms, delta H Hermitian times n plus n Hermitian delta H, right? Smaller than n square. Can you see that? On the left-hand side, we have the two terms multiply two terms. We got the four terms, right? Right-hand side still the n square, n norm square. No problem? Okay. So let me see. do we have dart H? I need to double check, is that correct? Yeah, and then we can cancel each other, n squared, n squared. We can cancel, right? And also we can move the dart H squared to the right hand side. So you can say here probability and the dart H Hermitian n plus n Hermitian dart H and smaller than minus dart H squared. Okay? Right? I move the dart H to the right hand side. This is minus sign. And look at the left hand side. Dart H Hermitian. So dart H Hermitian, I should put the parentheses. Actually, I should this one. The dart H. Actually, dart H is two separate. Dart is C minus C hat, right? H. So all here I should write like this way. This is a dart H. Right? Dart H. This one. Dart H. Dart H. Okay. Dart is 1. H is single, right? Dart is equal C minus C hat. And what's the left hand side? It seems to see that, okay, you got the A if you look at A dart H as like A Hermitian B plus A multiply B Hermitian. What's the meaning of that? So that I give you another knowledge. So if we say the A oh, what happened? Let me see. Yeah, A Hermes. Oh. What's wrong with that? Does not work. It does not work. Let me try to. I cannot remove it, so I don't know what happened. Okay, forgot that. I need to rewrite. I don't know why I cannot. Probably this case. No. Why? Okay, I write right here. That is A Hermitian plus B Hermitian A. So this is equal to double real A Hermitian B. What's the meaning of that? So I can give you another property, that is X Hermitian plus X, or S conjugate plus X. It's better. No response. I know, but the pen does not work. Let me try to figure out. It's really bad. Does not show that. Let me see. I put it here, a new page. This one equals double real A Hermitian B. You may wonder, so A Hermitian B is actually a one signal or one symbol on one complex value. Equivalent to say that you have the X conjugate plus X. That gives the two real of X. Do you understand? That A plus JB plus A minus JB, so that is two real A, that 2A, right? Equivalent to say this one, you can see is the same thing, that is two real A Hermitian B. It's also, you can write like this, This also can be written like the two real AB Hermitian. It's the same thing, right? You just take the real part and doubles, okay? So if you know this one, so then we can go back to see the page 5, and let me see. I'm not sure it's the reason does not work for this. This one does not work. I don't know. So we can just continue to write here. The probability, this one is equivalent to say that we have the two real, and then n Hermitian, not working again. A Hermitian dot H smaller than minus dot H square. This step. Let me see. Okay, and then make it smaller, so you can see that clearly what I'm writing here. Is that right? That is because that is the form is like the x complex, x conjugate plus x. That is two real x. So that's why I say two real x smaller than the minus dot H square. And that's exactly what I write here is equation 12. You can compare that one and this one. What's the difference? No difference. The left hand side is this one, two real n Hermitian dot H. Right hand smaller than negative dot H square. That is also the dot H Hermitian times dot H. So that's given by this one value. It's the same thing. Okay? Can you follow that? That's equation 12. So far, it's mathematics, and also if you can accept equation 12, then you need to really understand what's the meaning of equation 12. Next step, because look at left hand side. You got the whole thing is like the random variable because you have delta equals c minus c hat. C hat happens because you already did the detection. That means c hat is finished. C hat is given. C was sent from the transmitter is passed, right? So it's also given. C and C hat are both given, although probably you don't know the true value C, but C already there. So that means the delta equals C minus C hat is given, is constant, not variable. H is given. We mentioned in the beginning here for given H, okay? Look at this one, for given H. So basically seeing that delta H here are constant. But N is noise. Noise is random. You don't know, right? It's random, this is a random variable. Basically the whole thing on the left-hand side is a random thing. Random variable. Okay, it's a random variable. You may want n Hermitian. What's the meaning of that? It's the row vector. n1 conjugate, n2 conjugate, n3 conjugate, because you take the conjugate transpose, right? So that's why you got the noise vector. The row times a column. So it's still the linear Gaussian. That means n1 is Gaussian, n2 is Gaussian. You times the, for example, the a1 plus a1 a2. So a1 n1 plus a2 n2 is still Gaussian. Linear Gaussian is still Gaussian. So that means the whole thing on the left side, you can call that is x. So this thing is called x. X is Gaussian. The Gaussian, if the Gaussian, first you need to know its average value, 0, because noise has 0 value. So this is 0 value. Secondly, you need to know its variance, the variance. Because the noise variance is n1, n2, this variance 1, but you have the scaling factor delta H here. For the noise here, it's not 1, it's assumed that it is the sigma square. The noise is sigma square, but the sigma square times constant delta H. So that is, you need to multiply this delta H square. That's given by this term, right? This is like the delta H norm square. The sigma square double, because you also have a 2, real 2 here. So that's 2 sigma square and delta H square. So that's the variance. So basically what I'm seeing here, if you look at the the whiteboard, I say that the whole, I use the red one to highlight. So this one is called X. X equals 2 real n Hermitian delta H. And X here is Gaussian, and average of X is 0. Then the mean value is 0. The variance of X is not 0. It's 2 sigma square and delta H square. So this is sigma, this is delta, this is a triangle. I should be clearly. Do you understand? Because firstly, the real noise, because noise is complex, and the real part is sigma square, the variance, and times 2 sigma square. And also you times the constant delta H, so that's why delta H square. Before the variance, you know the variance of AX is A square X, A square variance X. So that is another general property that is, how about the variance of the AX? That's equal A square variance of X. So this is a general property, right? I assume you know that. So that's why the A is like the delta H. So you got this one, okay? And then you say this is like the complex Gaussian. And now you say, okay, I replace this one by the X, okay? So it means that I want to calculate, I remove this one, is X smaller than minus delta H squared. All right, so that's what I'm trying to do. Okay, so then I want to add a new page to rewrite this last step. Probability X smaller than minus 1. Probability X smaller than minus delta H squared. I want to calculate, let me move to this page. I want to calculate this probability. That's the, okay, move to here. That's the last step, right? X smaller than minus delta H. And X is the Gaussian distribution. We just mentioned X is the Gaussian distribution. The average mean 0. The variance is 2 sigma square and the delta H square. That is the variance. Okay. Now, if you look at the Gaussian distribution, you're like given by this, and if you say X smaller than minus t is, for example, this is like this one is minus t, so it's smaller than minus t. You couldn't say that you got the larger than t. It's a symmetric if you look at the Gaussian. So this one is equal to probability X larger than the positive delta H squared. Because look at this one and this one, they are symmetric around the y-axis, right? So then next one, X is Gaussian distribution with 0 mean and this variance. And we need to remind this is a Q function here, this one. And then what's the probability larger than this value? We can use this property, right? Okay, this is a Q function larger than threshold. This is threshold. What's the threshold? Threshold is delta H squared. That's also called a small x. Okay, that's delta H squared minus mu. Mu is 0. Divided by sigma. Sigma is the variance. The variance is this one, right? That is that is this one. 2 sigma square delta H square. This whole thing. Can you see that? According to the equation 6. X is Gaussian with the PDF given by above. We know this variance. So this is square root of the variance. The threshold is t. T is the delta H. So we can get this formula. And then you can get a further step. If we move a little bit above, we can write like this one. Because delta H squared on the above of the denominator, so we can put together, so we can cancel part of them. So that is, I think it's, let me see, it's the same as this one. Square root delta H and the 2 sigma square. Is that right? So because del H squared put inside of the square root, that would be del H power 4 divided by del H power 2. That we get the cancel each other. So you can get this step. That exactly equation 14. Look at the left-hand side. Okay. So that is, do we finish? Yes. That is equation 10. Equation 10. Because delta is c minus c hat. We put back. So that is equation 10. So let's explain the equation 10. So we just go step by step to solve this equation 10 and find out the error probability. And this error probability is related to the delta. H you cannot change, right? H are given. Sigma square is not very given. So that's a delta. Delta, that means the code word difference. And when you design a code word, so for sure you want to make sure this error, sigma c hat, if they are the same, that means you got the correct detection, there's no error. Sigma c hat equals 0, then probably error is 0. But it's not equal to 0. And remember, Q function is a decreasing function. If you have the larger than, for example, Qt, if T larger and the Q is smaller, right? So that's decreasing function. So for sure, you wish the delta is as large as possible. If delta is larger, then Q value is smaller, right? Because Q is a decreasing function. So delta is larger, then you can get a better, smaller error probability. So that's why we design the signal. We wish their distance is far away as possible because we want to make sure they are separated. They have the good separation. So the same, likewise, the sigma c hat, if they are not equal, so please just keep them with larger distance to each other. So then we can make sure this error probability is small. Okay, that's the physical meaning. So the next, because of the limited time, I'll skip quickly, okay? I cannot, like the step-by-step to teach you some fundamental statistics. So for the fitting, I can explain to you briefly, not in the writing. Based on the equation 14, so the question is, okay, you're given channel. How about channel is fitting? Okay, if channel is varying, then usually how you can calculate the error probability. You need to take the average. You take the average of 14, equation 14, with respect to the average realization of the channel H, because H is changing, H is random. So you need to take the expectation of the equation 14 with respect to the H. Theoretically, you take the integration of 14 times its PDF of the H. So that is called the average. Do you understand? So I think it's very similar to the ergodic capacity. Look at here. You know this is channel capacity. It's for a given channel. How about a random channel? You need to take the expectation of the whole thing with respect to the H. H is average. It is varying. It's channel. So when you calculate this expectation, you need to take the integration of this thing with the PDF of H. So that's a theoretical value. Okay. So likewise, here we need to take the average of H. So first step, we need to simplify. How do we simplify? I go quickly. So that means, firstly, we start from here, right? So delta H. Delta H could be written as this formula. That first step, you can see that's clear, right? That is like the x squared equals x Hermitian times x. This clear, okay? This have no problem. And if you look at in the middle part, delta H times delta. So that is one is actually can be decomposed by the SVD. So we look at this one as the whole thing, delta H equal delta as like this one. And its SVD decomposition is given by this one, V Hermitian lambda V. You may wonder why it's not a U Hermitian lambda V, because SVD usually U Hermitian lambda V, because it's like symmetric. So it's the U equal V. So that's why you got a V Hermitian lambda V. You substitute into this equation, so you can get this formula. You can this step. This so far is still simple calculation. It's still same. And now you define the new one like B as this column. Then you can got the B Hermitian lambda B. Lambda is the diagonal elements. B is a column vector, and B Hermitian with row vector. Now you say a row vector, the diagonal, and the column vector. So altogether, there will be summation of the beta. Beta is the kth element of B, square of the lambda. You can see one row, one diagonal, one column. So they multiply each other. That will be the same answer like this one, right? Or the sum square, lambda. And this one, if you look at equation 15, and on the lambda k here, what's lambda k? Lambda k is the singular value, this is SVD. SVD means a singular value decomposition. So lambda is the singular values of this code word difference matrix. These are constant, so lambda is constant. So this constant, what is B? The beta. Look at here, B equal VH. H is random channel, random, and H is a complex Gaussian. V, just the unitary matrix, is constant. Unitary matrix does not change the PDF. So you can just regard B is the same as H. That means statistically, they are the same. They have the same property. But look at the real value. The value, they are not identical to each other. That means B is random, H is random, but they share the same property. So the B here is also complex Gaussian. That means beta k is a complex Gaussian. And the beta k square, remember I mentioned before, if the complex Gaussian is a magnet square, that's a Rayleigh distribution. So that's why beta k square here is a Rayleigh distribution. So if you put this equation, 15, into the equation, this one, 14, so you can see here equals this value, or like the equation 16. You just put the substitution in there. So you may wonder why I get the exponential previously as Q function. So here I use the Shannon bound, like this one. Q function smaller than exponential half the x squared. I want to remove the square root. So that's why this one, I take the exponential and the square divided by 2. So that's why you can see I got this one. There's no square root. This is the Shannon bound, the first step. And second step, I substitute equation 50 into this one. I got this value, equation 16. And look at this one. Beta k, you can regard beta k as hk, because they are the same in statistics. They are both the complex Gaussian. And then hk square is the Rayleigh distribution. So we say h is a complex Gaussian, then the beta k is also a complex Gaussian, and the magnitude of the beta k is the same as the hk. This is a Rayleigh PDF. It's a general PDF, Rayleigh distribution with the PDF is given by this one. So remember, if we now for the equation 16, if we want to take the average, not average, take the expectation with respect to the hk square. So okay, we take the integration 16, and times it's a PDF. This is Rayleigh distribution. So that is the average. So now on the left-hand side, we remove the h, because we take the expectation of the whole thing with its PDF. So that is the equation 17. The next, we just solve this. This integration can be solvable. So we can solve this because this is like the beta, you can call the y, fy dy, this y square. So you can simplify this integration. Finally, you can get the equation 18. So I skip this calculation. This is just a mathematical calculation, not too hard. So the key thing here, why I make these changes, because I want to simplify that the beta k here is the same as hk. That is still complex Gaussian, so that's the critical thing here. H is complex Gaussian, the b, also beta is complex Gaussian, so that's why we can get equation 16. We know the distribution, we take the average, take the expectation, times this one. Okay, so that's it. So, and then we got equation 18. 18, that's the same as equation 11. So it tells us, look at the first term here, is SNR, right? 1 over sigma squared is like the SNR. And the power minus R. So now the key thing here is what's the small value R? Go back to see. The R is here. It is given by the number of non-zero singular value of the covert difference. That's also called the rank of the channel. The rank of the channel is the number of the non-zero singular values. So better, if you have a larger value of R, you have the better diversity order. Remember that somewhere we mentioned this in the beginning here. SNR power minus GD, that's R. R is better, larger, the whole thing is smaller. The diversity gain will much, if the diversity gain is larger, that means this red curve will be very steep, right? So it's better. So that's why we hope that R is larger as possible. And also this one called coding gain. That's the lambda 1 times lambda 2 is a product. So that means the product of these singular values. So from all the analysis, so these are the mathematical derivations, but in all you have to really understand, even you don't follow the derivation, but you still can understand that why we should do this. Why we do this analysis, because we want to find out some major insight. The major insight here is that, okay, the R is the rank, right? R is the rank of this channel. It's a matrix. The matrix is code word difference matrix. And lambda k is the key singular value of these code word differences. And we wish this R is large as possible. So now we can review some examples. For example, the arithmetic code. Let me see where is it. Yeah, arithmetic code here, C. If C is given by arithmetic code, you can see C here, if it is not 0, is always the full rank, unless it's 0. It does not have the case of rank 1, because you can see S1 is on the diagonal, S2 is also the anti-diagonal, right? You can try out all the possible cases, S1, S2, they all full rank, all full rank. Full rank means R equals 2. R equals 2 means the divergent order is 2. That is the largest possible value. Because you have only 2 transmit antenna, the order is at most 2. So you can always get the 2. So that's why today we say arithmetic code is not only better, is the best in terms of simple decoding, as last time we mentioned, single symbol decoding. But now today we say arithmetic can achieve the diversity order of 2, the maximum diversity order. You may say, okay, I can also do this thing. I transmit S1, and then again from second antenna. You look at this metric, it's still the diversity 2, because the full rank is diagonal. But this one is less efficient than this one, right? Because this time you use 2 time slots to transmit 1 signal, but automotive use 2 time slots to transmit 2 signals. So that means its rate is double of your scale, right? This one is also, we call it antenna hopping. That means the antenna transmits S1, next time slot, antenna 2 transmit S1. So for sure, that is, you can get a 2 version at the receiver. So you can get the diversity of 2 without any interference, right? Simple, but not efficient. But this one, very efficient. Okay, we have also other cases. If you want to talk about the 4 transmit antenna, there are many, more than 20 years ago. So there were some researchers working on these topics. How about for 4 antenna, they designed this code? Very similar to automotive, not the exact same one, right? So they also prove that, okay, they can achieve the diversity for the 4 antenna. Also, quasi-orthogonal, you can skip that. Quasi-orthogonal means that quasi means not real. That means very close, proximate. So this one, the main purpose of this one is that to increase the rate. Because look at the orthogonal one, it has S1, 2, 3, no S4. If you add another S4, it's not a full rank. So that is like the magic. Only automotive can get the full rank, full rate. For all the more than 2 antenna, you never achieve the full rate. Full rate means that the rate 1. If you have M antenna, you transmit the M symbol, not possible. If you transmit M symbols, you cannot get the full rank. That means full order. So for 4 antenna, at most you can only transmit 3 symbols so that you can get the full order, full diversity order, 4. So basically this one, like the 4 time slots, 4 antennas, right? The first row is sent from the first antenna, second row is sent from the second antenna, third antenna, fourth antenna. But you see, I have to take a break in some time, right? 0. If you add S4, this is not full rank. It can be approved, okay? But this one, like you see, I add S4 on the anti-diagonal here. But it's not full rank. You can increase the rate for sure, but you lose your benefit of the divergent order. You can achieve this here. This encoder, you can forget that one. So the star curve is a quasi orthogonal. That means that this one, equation N19, you see it's slope like this, because it's a divergent order is like the 3. And this one is equation, this equation, that's the orthogonal one, the circle one. So that's the difference. Okay, so I think that we spent a lot of time to talk about the MIMO. So the major thing is equation 1011. That is, we try to analyze the error probability. We want to reach conclusion that is, on the average, so the error rate performance is decided by this figure, this equation, GD, diversity order, diversity gain. Diversity gain is given by this rank of the channel, of the code word. And you may see automotive here, C, is given by here, right? So this is automotive code, the C. Its rank is 2, is maximum, because you have 2 transmit antenna, so maximum you can only have 2. So that is depends on the rank of the C. I think that's the major conclusion about this part. Okay. We still got time. I want to go to the topic of them, because here is just some the story, not too much mathematics. I think I can talk about this one. Can we skip the break if you don't want? So then we can get more time to talk about this topic and review, okay? If you're happy, okay. So for OFDM, I think this is only story. You can relax a bit. It's not too much derivation, right? So this is a long time ago. So actually, this is a Taiwan researcher. I think this he studied in Stanford. I read his paper when I was studying this OFDM, and later he joined the Bell Labs. He published the paper and filed U.S. patents on the OFDM. But at that time, his invention did not attract the attention. Why? Because there's no hardware, no the advanced, that means the hardware implantation. So it's still the theoretical research. And later, 5 years later, so FFT was considered, was invented. That, I mean, that you know the DFT, right? Discrete Fourier transform. But in order to implement DFT, so later they invented the FFT, the fast Fourier transform. They called the butterfly algorithm to make it very fast to compute this DFT. And then later they can be used to the OFDM. And also the 1985, the Lance Simony, he's also the researcher in Bell Labs. I met him many times in the conferences. He just retired last month from the university. He's a really good guy by adopting the OFDM into the mobile communications when he studied this topic. And then in the 1990s, the OFDM was so popular and widely used many standards in Europe, and then later in the IEEE, you may know that L211, right? That is your Wi-Fi, right? We have different versions of Wi-Fi, 11A, 11B, 11N, 11P, many other new versions so far. And then also it was extended to use for the WiMAX, and also for the N11N, that is multiple antenna of OFDM, and also L2.22 standards, 3GPP, LTE. So I think nowadays all the standards for the broadband communication use the OFDM. Yeah. Then what is OFDM? OFDM is actually a multi-channel modulation, divide the channel into the many parallel subchannel. Very familiar, right? Sounds very familiar. So we got topic called the parallel Gaussian channel. This one. This one. This is like the OFDM brief model. We have parallel channels, and each channel is noise and signal transmission. You may wonder, where is the fading? You know, the OFDM is great thing that is it can just ignore fading. Why? Because it splits the broadband channel into the many narrow band channel, and the fading does not appear in that narrow band channels. So I can just roughly show you this one. So for example, let me see. Yes, good. This frequency channel, if you look at this channel, frequency selected channel, you know frequency selected channel, right? This is like the channel gain H, magnitude. And it's for the broadband channel, so it looks like the frequency selective. For the narrow band, it's always this, like the smooth, there's a narrow band channel. It's like the flat, very constant. It's not, that's called a frequency non-selective. But for the broadband channel, all the channel behaves like the frequency selective. You may wonder why. Because for the broadband, we have so-called multi-pass fading. Multi-pass. Multi-pass means that, okay, I send a signal from here to you, this is direct pass. And also the signal goes through that wall, reflect to you. The second pass, third pass, fourth pass. If you have many multi-pass, right? That's why. You may wonder, for the narrowband, why we don't have? Because for the narrowband, the transmission rate is very slow. There are still some multi-pass, but overall, they arrive at the receiver almost at the same time. Because their transmission rate is slow, that means their arrival different. It still say, okay, we have the signal symbol is like this. And the second one is like this. And the third one is like this. There are still some, the delay in the symbol. If this is one symbol duration, second symbol duration, third one, this is a reflected pass, right? They are almost the same because the transmission rate is so slow, that means they do not overlap each other. It's still one symbol. But for the very fast data transmission, then I use the blue one, then you can see the difference. Let me see. You see, because for the very fast data transmission, so the path duration is so narrow, and because we've transmitted so quickly, right? And duration are very small. And then if you still have the delay, then you can say the symbol, the first symbol may be overlapped with the second symbol. This is the next pass, second pass. This is a direct pass. This is like this one, and this one. Okay, so that's the reflected pass. You can see you have a two-way to arrive at a receiver, right? So the pass train go to directly, the pass train reflected to the receiver, and then they will overlap each other. The signal will be, this one is like the S1, S2, S3, S4. This S1, S2, S3, S4. You see here, S2, S3, they overlap, S3, S4, they overlap. So that means they call the interference, called inter-symbol interference for the broadband communication because they transmit so fast. For the narrowband, they do not have this problem because they transmit so slow, the duration is so big. So you can see they still have the difference, but it's still one symbol. It's still one symbol, doesn't matter. So that's why if you have the time separation, so in the frequency domain, take the DFT, it's like the frequency selective. This one is flat. The OFDM, why it is good is that for the frequency selective channel, it uses the many subband to split. No connection again. So that means this chop this broadband channel in many division. How many for Wi-Fi we are currently using every day? So it is 64 DFT. It has the 52 subchannel for the data, another one for the dummy channel. So that means the OFDM, the given bandwidth actually is split into the 64 divisions, plus another 16 for the guard interval. Okay, that's OFDM standard. And for the DVB, digital video broadcasting, so we may use a 2K mode or 8K mode. 8K means that you 2048 DFT, point DFT. That means the whole broadband channel is divided by the 2000 division. And each division, if you look at the magnitude, it's almost flat, right? Overall, you say it's frequency slightly. However, if you just look at one subchannel, one division, it's almost flat, does not change too much. So that's why it's like the parallel Gaussian channel for each subchannel of OFDM. So that's why we say OFDM, that is a parallel subchannel with subcarrier. And then this signal are sent in parallel together. It's current to see this Gaussian, X1, X2, S3. Different signals are sent at the same time from different subchannel of OFDM. Okay, so that's why. And why do we use OFDM? Too many advantages, right? Efficient and the parallel subcarrier are orthogonal to each other, and also robust to the multipath fading, because we use the called the cyclic prefix. Later I will explain to that. We use some the cyclic prefix like the Gala interval, and also easy to implement in hardware because we can use the DFT. So we can see this is a typical implementation of OFDM. So this is a typical modulation. 0, 1 is mapped to the QPSK, BPSK, or QAM. And then you can ignore this. Partly it certainly means for the channel estimation, you need to add some training symbol in the beginning. So you can ignore it, doesn't matter, that's not related to the course. And then these signals transform through the RFFT. Is that like you have the many signal for your QPSK, you generate the 1000 QPSK symbols. Now you just group every 64 in one vector. Every 64 in many blocks, right? For the first block of 64, you put it into the DFT, the input of the IFT. And then after IFT is like the DFT, okay? Mathematically it's DFT. And then you got output, it's still 64, right? And then you add a cyclic prefix. Cyclic prefix is like the overhead, is like a head. Why is it called a cyclic prefix? I can give you the simple example to explain to you. Let me see the whiteboard. Where is it? Okay, here. So after DFT, for example, we have 4-point DFT. We got output. The cyclic prefix like this one. First, I still keep the x1, x2, s3, s4 in that vector. And then next, I need to pause again, rejoin. I don't know. And then I add S3, S4 on top. Because I copy these two on the top. That's called cyclic prefix. I copy the bottom 2, 3, 4, depending on the number of the given values. I copy the bottom part and add on to the top. That's called a cyclic prefix. You may wonder, why should we do that? First, you add a cyclic prefix, then that block is longer, right? For sure. This cyclic is like the protection. Protect because the signal anyway, the block will be sent out, will be corrupted by the noise or by the symbol interference. So the interference only happen on the beginning of the block. So that means this part will be anyway. This part will be interfered. So that one will. This one is usually the header part will be interfered, will be affected. So at the receiver, we just discard it. It's like the protection. Before, I think that sometimes you look at the launch of the spacecraft, then they have the also protection cover on top, right? Once it's launched successfully, the protection cover just drop off because it's only served for the protection, and then discard it. That's it. So this CP, cyclic prefix, serve the same purpose. We add a redundant part on the top, and then once it's corrupted, interfered, Forget that, we just remove it, because anyways, these are redundant. We still have here. These are our useful information. These are redundant, the cover on the protection part. So that's why on the receiver, you can see we remove that part, because this part has been crafted, has been affected by the feeding noise. Because I mentioned that usually only the block, the top or the beginning of the block was affected. If you further ask why, okay, derive the signal transmission model, you will see what happens. So I don't want to bother to talk about that mathematical part. I just want to give you the reason why we want to add this one, because we want to protect the block, we want to protect the useful data, and then at the receiver, once we remove it, we still can get a clean version of the signal. Okay, that's why. This one shows you why we have the multipath feeding, because the signal was sent out and reflected. In time domain, it looks like we have the direct path, reflected path, or multipath path. And this intersymbol interference is called the RSI channel. Here I want to skip the details, because this duration is, will take at least 1 hour. So I don't want to bother to talk about this transmission model, math view. You can skip this math view, okay, due to limited time. I just want to give you this, you only need to focus on this one, this block diagram, to know its principle. If you want to really go to the math detail, it takes a lot of time. Usually it takes about 1 hour at least. We need to explain first what is RSI and why we can derive this model, and then how it can be transmitted, and then how it can be received at receiver. I want to skip this due to limited time. So anyways, then talk about the MIMO-FDM. MIMO-FDM, that is currently we use multiple antenna, and 1 antenna, 2 antenna, 3 antenna, M antenna. Remember, OFDM actually, if you look at the function diagram, it's like this one, FFT, CP. I think that's the core part of the OFDM. On the transmitter side, okay, block transmission with IFFT plus the cyclic CP, cyclic prefix. On the receiver side, remove the CP, and then FFT, and then detection. That's it. So that is a typical block diagram. And then, okay, so then for the MIMO-FDM, usually we say, okay, for each antenna, we just add the OFDM transmitter block. That is the DFT, inverse DFT and CP. Inverse DFT, CP. A receiver remove this one, and DFT remove CP and DFT, like this. And modulation goes to the speed and block coding. For the automatic code, the first row go to this one. The first row go to the OFDM. Second row go to the second OFDM. So that is a MIMO-FDM. I think there are a lot of benefits for sure, because MIMO has benefits in terms of the capacity gain, diversity gain, and OFDM is great in terms of its very band efficient. It can send the data through the sub-channel in parallel, and also it can overcome the frequency selective feeding. As we mentioned, that the frequency selective feeding is split into multiple flat feeding channels, so that's why it can have such a benefit for OFDM. Then that's why we use MIMO-FDM. The standard Wi-Fi, the 11N, is based on the MIMO-FDM. Okay. For this one, I also want to skip. I think that in the project you may come up with some speed encoding for the multiple antenna. I want to skip this one. Okay. We still have some time. I want to take you back from the review, because I think definitely you may be more interested in that, the final exam, right? So then for the whole course, what do you really want to test us, right? So it's not easy to come with a question. So you just imagine, can you have the paper of the multiple choice question? Okay, if I give you the task to you, so how do you give the multiple choice question papers? Not easy one, right? So that's why our paper, if you look at the course outline, I already mentioned this final exam. Not here, probably here's final exam. Okay, 5 to 7 compulsory questions in 2 hours. definitely it's not multiple choice question. It's like some the analysis, the derivation, calculation, something like these big questions, right? Something like that, not multiple choice questions. Okay, 2 hours. So that's why I want to take you back to take some of the key point, because we have. Okay, still, let me see. Yeah, I want to take you back from beginning. Let us see what can be, which part may be useful for your preparation for the final exam. I think, let me see. For the random, this one definitely is a basic knowledge. I don't want. It's not part of the final exam, but it's basic knowledge. Probably you need to use that, right? But I cannot give the exam question on this topic. But definitely some of the fundamental knowledge. So skip the lecture 1 is just the basic. Okay, information theory. I think this is quite the good topic for the exam, because it will test you some of the understanding of the concepts of the information theory. And all these are automatically recorded, so you don't need to take the recording here. So after the class, you can watch the recording from our lecture, right? So every lecture is automatically recorded. You go to the Moodle page, you can download the lecture recording. You can watch every class, okay? I think here, stories, you can skip a story, right? First, you need to focus on the key concepts and the key result, like the theorem result. I think that also may be the really core part to test you. For entropy, definitely definition I will not give you them. I think for example, chain rule theorem definitely is really important, because it can be used to analyze something. So if you have no clue about the chain rule, like this one, this property, you cannot go further. I think the theorem 1, how you can prove it, and how you can calculate this such a table, and also the Venn diagram somewhere. I have the Venn diagram later, right? I also have the Venn diagram like this one. I think they are all quite useful takeaway knowledge, right? So you just go through quickly, and the theorem 2 is the major result connect to the mutual information. And multiple random variables are also important, but depends. Because this is quite general. This is quite general for the n dimension. Probably I'll give you specific examples, right, to say how they are connected in terms of the entropy or mutual information. Inequality may not know, because this is advanced knowledge. Okay, so this is about the information theory part. And the coding part, I think because we have only 2 topics, block coding, convolutional coding. For the block coding, I think not too much information, right? So you probably just given the Hamming code, you are going to, for example, this one, how you can perform the syndrome decoding. You are given the receive signal code word, and then how you can recover the code word. So according to this page, right? If you truly understand, I think this is the key part for the block coding. And also for the Hamming code, that is what is the Hamming code? For one way, how you can contrast Hamming code. Secondly, how you can use the Venn diagram to perform the decoding. For example, like these 2 questions, if you can perform very well, then the Hamming code should be fine, right? And for convolutional coding, that is quite complicated, because convolutional coding, first you need to draw the encoding diagram, right? For example, you are given these examples, and then how do you, first you need to make sure the first step is correct. You draw the correct encoding diagram. If your first step is incorrect, then the following will be all wrong, right? So first you are given, for example, you are given the vector representation, then how you can, I think that's 101, this is one representation, right? So once probably you are given these vectors, then you immediately, you can, based on this left-hand side, you can draw the right-hand side. You know, they are connected 1 to 1. G1 is the first U1. G2 is the U2. You can see here, 101. So probably I'll give you different examples, right? 101, 110, or probably got a G3, G4. You never know. So I just want to test you, hey, if you really understand the vector representation to construct the convolutional encoding the structure. So this one. Once you have this one correct, I think this is the first step. But that one, how do you can construct this table, state transition table, based on that knowledge, based on this one. So from here, you can see this state. You have two states, so that's why you can have the two block, that means 4 states together. And then for each state, you may have either 0 or 1 input. Then you can derive what's the next state, what's the next output signals. And also from here, you can draw, from this table, you can draw the state transition diagram. And then from there, you put it in the x-axis to stretch as a trellis diagram. Once you get a trellis diagram, you can perform the Viterbi decoding based on the trellis diagram. So this is a trellis diagram, and from this one, and then I'll give you, for example, okay, this is received the signal sequence. Use this trellis diagram, how you can perform the Viterbi decoding. Okay, so that's why we go step by step to perform this Viterbi decoding. So this part, convolutional coding is not easy one because every sector is like a chain. You have to make sure every sector is correct. Then you can go to the next one, right? From the vector, from the diagram of the encoding to the state transition diagram, table, chart diagram, Viterbi decoding. Every step should be totally correct. All right. So that I think this is a bit challenging part. Let me see, capacity. Okay, capacity also mainly tests you truly understand the question like this one, example 2. If you can do this question by yourself without looking at the paper, okay, I think that's fine for you for this part. So that means you really understand how to calculate the mutual formation. And if you are not familiar with the part, you have to practice, okay? To follow this derivation to calculate one by one. So mutual information is just the first step, and then based on that one, if you can prove the theorem 1 and the theorem 2, that would be great. That means it's still another calculation. Theorem 3 may be too complicated for you, right? Because I mean the calculation is complicated, but the principle is still the same. Okay, so that means this part mainly to test you how to evaluate the mutual information or the capacity of the channel, right? So you should truly understand how to go step by step. You should have this grasp this technique. Gaussian channel, I think that mainly the concepts, right? So I think the major thing, not here, major thing may be the water filter solution, this part. Because before this Gaussian knowledge channel, the only thing I think is theorem 3 may be important. I mean, can you derive by this formula by yourself, right? Capacity given by the maximum of mutual information, how you get a step, equate this page. This page is important. You can write it by yourself, okay? Then that means you should understand what is the capacity of the knowledge channel. Right. And then based on that, then you can further say, how about the parallel Gaussian channel? So can you get this solution, like this page? Can you truly understand and write it, right, for the parallel Gaussian channel? And draw this diagram to show this water filter solution? I think this topic is mainly limited to this water filter solution and Shannon channel capacity. On MIMO, I think I already mentioned that is, forget this definition. I will not test your definition. Let me see, MIMO channel capacity. I think this equation 6 is critical. In the break, I know that student, we just discussed this channel capacity. I found sometimes you may not know this formula very well. You know the meaning, but you don't know when to use, when not to use. So the reason is that you don't know how it comes from. You have to go to the beginning to see how equation 6 can be derived. If you truly know where it comes from, how it can be derived, then you know how you can apply, right? I think that part is critical. And then this part is only simulation for the project, so I will know. I think that's only for the project only, this part, ergodic and RTG probability. 10 spectrum coding. Spectrum coding part, I think the orthogonal code important, especially I think the two things. One thing is that the this page, page 14, decoding automatic code. So how is the automatic code decoded, right? You need to show the step by step, not too many steps, but you can write it by yourself. That means you appreciate, you really understand this automatic decoding, right? That's especially from equation 1 to equation 2 to equation 5, okay? All the steps, you should be able to write it by yourself, okay? The second part, I think that is the PEP analysis. That is, you may not, that means maybe from the equation 12 to equation 16 or 18. Or 18, I think that is maximum, right? Only 3 pages. That means, first, as we explained too much about these 2 pages. That means for the first step, you should understand that is the error occurs when the minimum distance can be achieved for C hat, not for C. If it's larger than, then you will not get error because you always get the true value to be minimum distance. Then that would be the probability we will not call the 0, called error. It will be called correct detection, error probability. Right? Then all the following, which you can just watch the video of of today's class. You can follow step by step, and then you can truly understand. Final answer is related to this one, the rank of the channel. Okay, this combined, very similar, same as equation 11. I think this part, and for the orthogonal code, you may understand why it's orthogonal. We say this O means the orthogonal STBC. This orthogonal means it's similar, it's the same as the automotive code because they are orthogonal because the matrix is orthogonal. That means if the matrix itself times Hermitian, it can lead to the diagonal channel. So if you remember for the automotive code here, we got this one, right? Due to the code word you can also write like this: C Hermitian times C. What happened? It will be S1 conjugate S1 squared plus S2 squared, right? In the diagonal. So it's the same thing. You can see here we got this one diagonal. So that due to the automotive, due to the orthogonal, you have. So this one is called orthogonal. Okay. So that's why for the other, why this is called orthogonal, because the C4 Hermitian times C4 is a diagonal. But for this one, it's not orthogonal. It's called quasi. Quasi means not real, right? It's close, but it's not. Why? Because it's Hermitian times C, not a diagonal. You can try. You can write like this way. You can write it out. Okay. And then the final one today is OFDM. We just briefly talk about because I think OFDM can be used in the project. If you choose the project of OFDM, yeah, this part may be useful. And but this part is not easy to give you the exam question. I cannot just let you derive all these details. This is not an easy one. I think that you just know what happened. If you really truly interested in the OFDM, you can choose that project. We have the one project, at least one project. It's about OFDM implementation and with the coding, called the coded OFDM. I think that should be fine. Okay, so I think that is the whole course. I'll just take you to review. I hope that you could get the key points and then go back to watch the video lectures. And then we do not have the past paper to give you to practice because these are all the big questions. And I think time usually is sufficient, 2 hours sufficient. The only thing depends, if you can do everything, 2 hours is sufficient. If you cannot do any question, it's still sufficient because you have a lot of time not writing anything. So anyway, so I wish you good luck in the final exam, and I hope you really learn something from this course, okay? That's it, thank you. Yeah.不会，我主要看不太，主要看那个 logic flow， 顶多会扣很小的分，不会扣那么多。
老师考试的时候，一些公式它会写在那个不会。